So section 5.4 deals with two things that we use integrals to do. One is to find the average value of a function, and the other one is to be able to find the area between two curves, which is very similar to finding the area between the curve and the x-axis. So we're going to kind of get into that today. So as far as the average value goes, the average value is basically simply that. The average value of a certain number of things given some sort of, function value, I can determine what the average overall value would be, given between two values. And essentially, they go through all this stuff here. The whole formula behind, the average value, whether it be average height, average anything, I'm going to do 1 over b minus a times the integral from a to b of f of x dx. They basically say it's basically analogous to averaging n numbers by adding and dividing by n. So it's kind of a quicker way of doing that, especially when you have circumstances where you don't have a function that's going to really produce integers for you. So case in point, if you're asked to find the average value of f of x equaling the square root of x from 0 to 9. So, you have, this is a continuous function, and I have basically an infinite number of numbers between 0 and 9. They're not all integers, mind you. But if I took every possible number between 0 and 9, plugged it into the function, got a value for f of x, and averaged them all together, that's what I'm looking for here. So the average value for this is going to be, for me to evaluate this, I would do the integral from 0 to 9 of square root of x dx and multiply that by 1 over 9 minus 0. So I would get 1/9 times the integral of 0 to 9 of x to the 1/2 power dx. I would take the integral. I would plug in the 9 and the 0, carry through the subtraction, and I would end up with 2. So basically, from a graphical standpoint, they're showing you here the function y equals the square root of x. They're showing the area underneath that curve. They're saying that the average would be like the area in that rectangle. And if I go from 0 to 9 and I go up with a y value of 2, generally the area of that should be approximately the area that's underneath the curve. Approximately. It's the average area, more or less. So your turn. Find the average value of the following function over the given interval. So what is the average value of the function 9 minus x squared on the interval -3 to 3? So basically to do this, if I want to find the average value, I'm going to do the integral, or so I'm going to first get ahead of myself. I'm going to do 1 over 3 minus -3 times the integral of -3 to 3 of 9 minus x squared dx. This is going to be 1/6. This is going to be 9x minus x cubed over 3 evaluated at from -3 to 3. So essentially I'm going to have 9 times 3, which is 27, minus 27 over 3, minus 9 times -3, which is a -27, which I could just put that there, minus -27 over 3. This ends up being 18 minus a -18. 18 minus a -18 is the same thing as 18 plus 18, so I get 1/6 times 36, which is 6. So on average, the value of f of x for this function between -3 and 3 is 6. Now sometimes they're going to present this in more of a word type format. So for instance, after X practice sessions, a person can accomplish a task, that should just be a task, in f of x equals 12x to the -1/2 minutes. Find the average time required from the end of session 1 to the end of session 9. So what is the average time between these sessions? So the average time, given that f of x is a time function, is going to eventually just be the average value from 1 to 9. So I'm going to do 1 over 9 minus 1 times the integral from 1 to 9 of 12x to the -1/2 dx. So that's going to be 1 over 8. When I do the integral of 12x to the -1/2 power, I'm going to have 12 times x to the 1/2, because I'm going to add 1 to the exponent, divided by 1/2. Evaluate from 1 to 9. And that's going to give me 24 square root x. Evaluate from 1 to 9. So as I do these, I'm going to get 24 times the square root of 9, which is 3. So 24 times 3 is 72. Minus 24 times the square root of 1 is 24. This ends up being 18. 18? No, take that back. 48. And that gives me 6 minutes. So on average, the time required from the end of session 1 to the end of session 9 is 6 minutes. So as far as area between curves go, I mean, what you essentially need to be able to do is keep in mind that when you find the area between curves, you always want to do the area of the upper curve minus the area of the lower curve, or essentially you're doing an integral of the upper curve minus the lower curve. To do that accurately, sometimes you have to make sure you pay attention to, if they intersect, because sometimes they're going to say, okay, we'll find the area between the curves between these two values. If those curves intersect, then whichever curve was on top is now going to be on the bottom after the intersection point, and vice versa. So any intersection points can certainly complicate it. And sometimes they don't just state, okay, we'll find the area between two curves between x being this and x being that. They'll say, find the area bounded by the two curves. And bounded by means, okay, well, they're going to intersect and, probably at least more than one spot. I want to find the area enclosed by the two curves, so they should be between them in either case. But again, I'm going to have a circumstance where one curve is going to be above the other, and then they may intersect, and I'm going to have the other curve being above the other. So being able to graph, being able to find intersection points becomes, key for doing this as well. So, but essentially this is going over the same thing. You're going to do the area of the upper minus the lower. So for instance, if I want to find the area between y equals 3x squared plus 4 and y equals 2x minus 1 from -1 to 2. You want to have an idea of as to what the graph looks like, because if they would intersect each other, I mean, right now the y equals 3x squared plus 4 is the upper function, it's on top. The y equals 2x minus 1 is below that. So, the upper function and the lower function are very clearly stated between the values of -1 and 2. If they would intersect, though, there could be some changing in positions between which one's upper and which one's lower, and you need to know that, and you need to know where it happens. So, having an idea of what the graphs look like is important for that matter. So, as we see here, since y equals 3x squared plus 4 is above y equals 2x minus 1 always, so all I have to do here is set up an integral going from of negative 2 to 1 of 3x squared plus 4, the upper function, the quadratic one, minus the 2x minus 1. So I would simplify that a bit. And a little further. And I would do now I would do the integral of this. So I'm just going to treat this as like a regular indefinite integral. The integral of 3x squared is x cubed. The integral of 2x is x squared. The integral of 5 is 5x. And I'm going to evaluate this from negative 1 to 2. So I'm going to plug the 2 in, which is what you see on the left. I plug the 1 in, which is what I have on the negative 1 in. I evaluate, and the area between these two curves from negative 1 to 2 was 21 square units. And here they're talking about the importance, like if they start crossing each other, then obviously again, which one's the upper function, which one's the lower function, can maybe change during a certain interval, and you have to be aware of when that's happening. So find the area between the curves y equals 12 minus 3x squared and y equals 4x plus 5 from 0 to 3. A sketch shows the curves do cross. So to find the intersection point, we set the functions equal to each other. Because if they intersect, they have the same y coordinates. Since both of these are solved for y, I'm looking for the common y coordinate. So I set them equal to each other. I figure out what x is. I do get x equals 1 and x equals negative 7/3, but I'm only considering the interval from 0 to 3, so I only need the one that's between them. So again, what the graph is kind of look like, it's from 0 to 1, the 12 minus 3x squared is on top, and the y equals 4x plus 5 is below it. When I go from 1 to 3, the y equals 4x plus 5 is the upper function, and the y equals 12 minus 3x squared is the lower one. So when I do the area, or when I want to find the area of this, I'm going to do the area from 0 to 1 of upper minus lower, and then I'm going to do the area from 1 to 3. Notice how I have the two expressions in different positions. Because I'm always doing upper minus lower. So I carry through the multiplications and simplify a bit. I then evaluate the integrals. And I'm going to plug in the 1 and 0 into the first quantity, and I'm going to plug the 3 and the 1 in the second quantity. And when I work all that out, I get 32. So the area between the curves is 32 square units. So let's have you give this a couple of tries yourself. I want you to find the area between the two curves from 0 to 3, where your two curves are y equals x squared plus 4 and y equals 2x plus 1. So I don't start off with the graph first. I actually start off with finding any intersection points first, because I want to be able to know what that is if it happens. So I am going to set x squared plus 4 equal to 2x plus 1. I end up with x squared minus 2x plus 3 equals 0 when I use the quadratic formula. 4 minus 4 times 1 times 3, I'll deliver 2 times 1. This goes to negative 8. And since I have a negative underneath the square root, there is no real solution when I set those equal to each other. that also means that there is no intersection point. That means that one is always going to be above the other. Doesn't take much to realize when you look at the two graphs. Y equals 2x plus 1 does something along the lines of this. Y equals x squared plus 4 looks something along the lines of this. So if I'm going between 0 and 3, I'm looking for an area that looks a lot like this. That's the area I'm looking for. So they don't intersect. So basically, this one's the upper one. This is the lower one. So I'm going to be doing that the area between these two curves is the integral from 0 to 3 of the upper x squared plus 4 minus the lower 2x plus 1 dx. I'm going to simplify a little bit first before I start taking any antiderivatives. So I'm going to have x squared minus 2x 4 minus 1 plus 3 dx. So now when I integrate, I'm going to have x cubed over 3 minus x squared plus 3x. Evaluate from 0 to 3. Excuse me. I plug the 3 in, I get 27 over 3 minus 3 squared plus 3 times 3. I plug the 0 in, all those just become 0. 27 thirds is 9, minus 9 is 0, plus 9 is 9, so I end up with 9 square units. 9 square units between those curves. Let's have you try another one. This one's a little different because in this one here, if I set x squared plus 5 equal to 2x plus 5, well, the plus 5s would both cancel, leaving me with x squared minus 2x equaling 0, which I would get x times x minus 2 equaling 0, which means x equals 0 is a starting point, it's an intersection point, and x equals 2. So these coordinates would be 0, 5, and I'm just plugging it into either one of the two functions. This would be 2, 9. So if I look at a really quick rendition of the graph like this, do it here, it's going to be rather small though. 2x plus 5 looks something along the lines of this. At 2, 9 and at 0, 5 is where these two graphs meet. And what you would see essentially is that it looks like this. We're looking for this combined area here and here. So I can see when I go from 0 to 2, the line is upper and the quadratic parabola is lower. And when I go from 2 to 3, their roles are reversed. So when I want to do the area, I'm going to have first the integral from 0 to 3, or no, 0 to 2, where I have the line on top, so 2x plus 5 minus x squared plus 5 dx. And to that I'm going to add the integral from 2 to 3 of, now in that case, the x squared plus 5 is on top, minus the 2x plus 5. So when I simplify, I'm going to have the 0 to 2 of 2x minus x squared here, dx. Here I'm going to have the integral from 2 to 3 of x squared No rhyme or reason for it either. X squared minus 2x dx. So I'm going to evaluate these. The integral of 2x is x squared. The integral of x squared is x cubed over 3. I'm going to evaluate that from 0 to 2. Here I'm going to have kind of some of the same things. I'm going to have the x cubed over 3 minus the x squared from 2 to 3. So here I'm going to have 4 minus 2 cubed over 3 minus, if I put zeros in, I just end up with 0, plus 27 thirds minus 9 minus 8 thirds minus 4. When I work these out, 27 thirds minus 9. Well, 27 thirds is 9. So this all becomes 0. Here I have 4 minus 8 thirds minus 8 thirds plus 4. So I have 8 minus 16 thirds. And 8 minus 16 thirds is, it's not approximately, it is equal to 8 thirds. And that's square units. When you have areas bounded by curves, I mean, you're going to have more than one intersection point. You're looking to find out where these, what's the area that's being bounded by the two curves. So as an example, I have 3x squared minus 12 and y equals 12 minus 3x squared. The x values for the upper and lower limits of integration are not given, so we have to find them by setting the functions equal. So here we actually, they're not telling us to go from x value to x value. We have to know where the intersection points are and move from left to right. So we set these equal to each other. You get the 6x squared minus 24 equals 0. Which means x is negative 2 and x is 2. So basically when I solve this equation, I get two different places where these graphs cross each other. So the graphs do bind off an area. This goes into some of the logistics of it, but essentially what I do to try to figure out which one is the smaller, which one's the bigger. So the upper function is going to be 12 minus 3x squared. The lower function is 3x squared minus 12. So I'm going to subtract those two and take an integral of that difference. So I end up getting the integral from negative 2 to 2 of 24 minus 6x squared dx. When I take the integral, I get 24x minus 2x cubed, going from negative 2 to 2. Plug those values in, I get 64. So the area between the two curves is 64 square units. So they're kind of showing that here. Keep in mind, there's a couple of instances where maybe possible you have several areas bounded by two curves. So make sure you find all the intersection points. There's also going to be times that it is possible that, depending on the circumstance, if I have one that looks like where I can't really do upper and lower, what I have to do is kind of left versus right. You can also handle that as well. Most of the time they give you work here, it's going to be able to be handled using upper minus lower. So let's see if you could do this. Find the area bounded by these two curves. So I need to get an idea what this thing looks like. So I want to find the intersection points between these two. So I'm going to set 3x squared minus x minus 1 equal to 5x plus 8. Subtract 5x from both sides and 8. Divide both sides by 3. This thing does factor. So I get this, which means that either x has to be -1 to make this equal to 0, or x has to equal 2 to make this product equal to 0, which means that -1, and if I plug that into the functions up there, I get 3. And 2, 18 are points that, wait, something's going wrong here. Yeah, that should be a 3. So that should be 323. There we go. Those are the intersection points. So when I graph this thing, it's going to look something along the lines of this. I'm not drawing this to scale necessarily. The lines over here, and I would have part of it over here, part of it over here. So the bounded region looks a lot like this. That means that this one's the upper function. This one's the lower function. And since one's quadratic and one's linear, they're not going to, I'm really not expecting any more intersection points between the two. So it's going to remain upper minus lower. So I know that my integral, if I want to find the area, it's going to go from -1 to 3 of 5x plus 8 minus 3x squared minus x minus 1 dx. I'm going to carry through the subtraction. So 5x, this gets distributed. So I'm going to have 5x plus x, which is 4x. 8 minus -1 is going to be plus 9. And I'm going to have a minus 3x squared dx. So when I integrate these, I'm going to have 2x squared plus 9x minus x cubed, going from -1 to 3. And when I plug these in, I'm not going to show all the substitution. I do get 32 square units. So that's how you find the area bounded by two curves. If you have any further questions, please make sure to bring them up in class. But until I see you there, have a good day.